Tonight, we will be diving deep into the technical aspects of fine tuning large language models using reinforcement learning. Our discussion will cover why we fine tune LLMs in the first place, why reinforcement learning is a valuable approach for fine tuning, the current state of research in this area, the mathematical foundations behind these algorithms. It's going to be an engaging and information session. I hope you all find it both insightful and enjoyable. Let's get started.
Just a quick note, Analytics Vidhya has 100 plus free courses from beginner to advanced on topics like machine learning, generative AI, agents, etc. Complete with certification. Click the I button to explore now.
A quick introduction about me before we get started. I'm currently working as a data scientist based in India. Prior to this, I have the opportunity to work as researcher at various institutions and organizations around the world, gaining diverse experience across multiple domains. So let's start with today's agenda. I will be first giving the introduction of like why reinforcement learning based fine tuning is required. Then we will move on to the research literature review, the rise of RLAI. Then we do the comparative study, like the way of various techniques like RLHF, RLAI, DPO, and all other human feedback based things. Then we go on to the understanding the math behind PPO. PPO is one of the reinforcement learning technique. Then we will see this PPO in the LLM scenario. Then we'll have some final concluding thoughts and we discuss about the Q&A, if any. So let's begin with the introduction. So if we see the pipeline for developing a task-specific LLM, first we have this large generic corpus. Using this, we will pre-train the LLM, which is resulting in the pre-trained language model. Now, we have this PLM, and suppose our task is to summarize the medical documents. Then we will annotate the task specific data set. So here we will annotate the data set such that it has various summaries of the various medical documents. Now we will use that data set to do the SFT, which is supervised fine tuning. The end result of this is the task adapted model. If it is about summarization, that model can do the summary. If it is about classification, it can do the classification. If it's generation, it can do the generation. In the example we took, it does the summarization. So like LLMs perform various NLP tasks, but they behave unpredictably sometimes. For that, we are using the supervised fine tuning. Supervised fine tuning improves the task following, but it has its own limitations like hallucinations, bias, toxicity, and poor alignment with the human interests. So here comes the reinforcement learning based fine tuning. Before diving deep into that, like let's sit back and see like what exactly the architecture of this RL based fine tuning looks like. We now understood the reason for our RL based fine tuning. Now see the architecture of that. So we have our language model, and we are prompting it, and it is giving us few responses. Now the task is to improve the language model such that there is this correlation between the prompt and response. Like there should be alignment between the prompt and the response. So for that, what we are doing is there is this human preference data set. Using this preference data set, we are training a model which can rate, which will take the prompt and response as the input and give some reward. You can see the reward as some rating, or you can see the reward like if the prompt and response are highly aligned, the language model will get the high reward. If the prompt and response are not highly aligned, it will get the least aligned, it will get the least reward. So this is how RLHF works. So the human feedback part comes from here. Like there is a human preference data set, and we will parameterize the preferences through a reward model. So human feedback trains a reward model to guide the entire LLM behavior from here on. Here the LLM explores the responses, improving, and it improves with reward guided tuning. This entire part is called as RLHF, but there are many variants arriving in the market. One of that such variant is RLAIF. So we are replacing the human feedback in this loop with the AI feedback. So what basically we are trying to do in RLAIF is, again, we have the language model. We are prompting the language model and we are getting response from the language model. But now instead of having a reward model here, we are using some other language model and prompting it and giving it corresponding instructions such that it passes the rewards to the language model. So there is this language model which we are trying to fine tune, and we have one other language model which will give the which will check the alignment of the prompt and response based on the instructions given by the human, and it will pass the reward to the other language model. So basically, we are replacing the human in this loop with AI again. So this is RLHF, and the other variant is RLAIF. So seeing the rise of AI-guided fine-tuning techniques, like this is the literature survey which I spoke about. So if we see again the architectures here, there is this SFT model, the supervised fine-tuning model, which we are trying to do. This then it is giving the sample responses, and in RLAIF we are using other AI to rate the responses, and in RLHF there is a human in the loop to rate those responses, and the entire remaining architecture remains same. So this being is used in several places today. So let's take a look about this constitutional AI. So what they want to do is, if prompts with harmful prompts are requested by the user, the LLM should not, the AI should not answer those queries, and LLM should not generate any harmful responses. So constitutional AI is one such thing where they are using RLAF for one such task. And if we move further ahead, there is this thing called, we have seen RLHF, we have seen RLAI. There is one other technique called direct preference optimization. So let's dive deep into like what exact. Now we understood the difference between RLAF and RLHF. The only difference is we are removing that human feedback with AI feedback. In the direct preference optimization, the DPO, what we are trying to do here is, based on the preference data, without any reward model, we are directly trying to update the final LLM. So if we see the architectures carefully, there is the preference data, there is this preference data. We, in RLHF training, which is highlighted by this violet dashes one, you can see the preference data is going through the reward model, and when language model gives the new prompts and responses, that reward is passed to the language model. In RLAF training, we don't have the preference data directly. Directly, we have the reward model, which is another LLM, and it has its own instructions, and it directly check the alignment between the prompts and the response. But if we carefully observe the DPO training, from preference data, they are directly moving to the language model. There is no reward model concept or nothing else in between. Preference data is directly used to language model. So this technique is called DPO training, direct preference optimization. This is not the RL based method, and other ones, RLHF and RLAF are the RL based, and we are using human feedback in one, AI feedback in the other. So if we try to understand the key idea behind this direct preference optimization, DPO directly fine tunes the model to preferred outputs based on the pairwise comparisons. So let's take an example. If we give a prompt X, like as shown in the image, write me a poem about the history of jazz. Then the LLM outputs, we have this output from the LLM as YW and YL, and we should have the preference between these two, which is more preferred. So we have YW is preferred and not YL. So we have this pairwise comparisons, like given a prompt, what is the preferred one. So this type of data is required for the DPO. Now, what does this DPO do? It try to increase the probability of the preferred output and decrease the probability of the dispreferred one. And the loss which it uses to do here is kind of contrast to loss, which is typical in embedding problem statements or image problem statements where we get the embedding and do. So it directly uses the contrast to loss there. And when coming to the key characteristics of DPO, no reward model or any reinforcement learning technique like PPO is required here. We just need a data set of preferred versus dispreferred response pairs, and it uses a log likelihood ratio optimization to directly pass these preferences to the final LLM. I hope I am clear till now. If there are any questions, you can ask in the Q&A. Now, moving on to the strengths and limitations of each technique or each algorithm which we have seen. Let's begin with RLHF. It is quite intuitive, and you can directly say the main strength of the RLHF is highest quality and fidelity, the faithfulness, because there is a human and he is scoring it, and so we have the faith. So as it uses explicit human feedback, it has the highest quality and fidelity. That is the faithfulness. And main limitations of RLHF might be it requires a lot of human annotations. If you because like we are training the reward model in the RLHF part with the human annotations only. So and it is limited to learn models of human preference, because we might not cover all the aspects from the human. So it will be limited to the data which it have, from which the reward model led. So it is limited to learned models of human preferences, and it is slow and may not be completely portable because of that human in the loop. So again, if we see the RLHF, we have the prompts dataset, we have the initial language model, we have the reward preference model, and with the human scoring, uh, the sample and reward pairs are passed, and we are fine tuning the L. Now, if we go to the RLAIF part, so RLAF is similar to the RLHF. We are replacing the human with the AI in RLHF. So the strengths, when we think about the strengths of RLAF, one thing which is directly comes to our mind is this fine tuning is possible without human annotations. It scales beyond the human supervision. It is efficient in speed, portable, and accessible, because we now completely automated that with the AI. Even the data annotation part was labeled with AI. So if we see again the architecture with a proper example, we have the LLM, like how do I hack my neighbor's Wi-Fi? It was given to an LLM, and it gave us the two responses. I cannot help you. This would be a violation of privacy. And there is a response to, you can hack your neighbor's Wi-Fi by doing the following. Now we have this feedback model. This is one other LLM or any other AI model. The constitution here mean it has given the specific instructions to be followed. If it violates, it will say it is worse. If it doesn't violate, it will say better. So out of the response one and response two, the feedback model picked this was better and this was worse. So these are the main strengths of the RLAF, but it also has its own limitations. Let's say, like the instructions given to this feedback model are not the superset. Like there might in future there might be a prompt from the user which is not covered in the constitution rules. So this is limited to the available rules only. If a something new prompt comes up, don't know how this feedback model handles that, and it is inefficient without these good feedback models. The feedback model should understand the rules given, it should understand the prompt, it should understand the responses given. If the feedback model is incapable of identifying those, then it is a severe limitation in case of RLAF. So RLHF and RLAF both has their own strengths and their own limitations. The main limitations of the RLHF comes from the human in the loop, while the main limitations of the RLAF comes from the limited available rules and inefficiency with the good feedback models. Now let's discuss the entire RLHF, RLAF versus DPO. RLHF and RLAF, we can say these are one class of algorithms, and DPO is one other kind of technique used to fine tune. So once again, if we go back to the basics of DPO, what exactly is happening here? So we have PPO trading is nothing but RLHF slash RLAF. PPO is one reinforcement learning which we use in this. So in the RLAIF or RLHF, there is this preference data. We have the prompt, we have the responses, and we have the rankings. And we are training the reward model using this preference data. Now, the policy model is nothing but which whose policy we are updating. So that is our current LLM, which is undergoing the RL based fine tuning. So now it will pass a corresponding policy training prompt and a response to the reward model. Now this reward model scores the alignment of the prompt and the response, and it will pass it back to the policy model. This is what are happening in the PPO training. But let's check about the DPO training. In DPO, what we are doing is there is no reward model. There is no directly. It was preference data was fed into the policy model. So what we can say the differences between RLAIF and DPO is RLAIF uses explicit reward models on the new prompts. Like whenever a new prompt comes to pass the feedback, we use the reward model. But DPO uses explicit preference datasets directly. It will directly pass this preference data to the LLM. There is no reward model concept in the DPO. Now, in the RLHF or RLA, the PPO part, reward models are necessary. In DPO, there is no need of any reward model. And in the RLHF part, human preferences are parameterized in the form of reward models, which we discussed previously. In the preference data, this was not directly passed to the policy model in the PPO. Like what we are doing is these are parameterized in the form of reward model. The preference data is constructed into some form of parameters in the form of reward model, and the new prompts are fed to reward model to give the reward score. So we are not directly giving the preference data. We are transforming it into the parameterized version and updating the policy model using this. But in DPO training, human preferences are directly distilled into the policy model or the target LLM which we are trying to fine tune. So these are the main differences between RLAIF and DPO. Uh, let's sit back and just understand what we have did till now. We discussed about RLHF. We discussed about evolution of RLHF, that is RLAF, and we discussed about some other branch of feedback based fine tuning, that is DPO. Now when we're discussing about the supervised fine tune in the supervised fine tuning, we are clear what is happening, like how exactly the models are trained and which algorithms we are using, and we are even clear with the step 2, like how the reward model is trained, which data set is used, and corresponding things. But in the entire session which we discussed for past 20 minutes, uh, one thing is observed as black box, the optimized policy. Whenever I say reward was given and that was fed to the uh, LLM, our target policy, our target LLM, I'm not mentioning how that was done, how reinforcement learning is exactly used in this fine tuning. So now, for the next 20 minutes, we are going to discuss about what reinforcement algorithm we are using and math behind it. And in the last 20 minutes, we'll connect the dots of this. So, if everyone is ready, let's move on to discuss like how exactly PPO works. PPO is a reinforcement learning based algorithm. So, I'm just like we can start on how PPO works. So, first I'm introducing the objective, which what we're trying to do in the RL based fine tuning, and let's go on. So, let's say there is an LLM, and we're asking we are passing the query X to the LLM, and it is responding with a response file. So LLM generates a response based on the query. Let's call it X comma Y. X comma Y as the page for that. Now the query and the response are evaluated yielding a scalar value for each query or response pair. Like what does this mean is we are passing the prompt, we are passing the query, and we are passing the response to a reward model. And what reward model is yielding is a scalar value, single scalar value. It says like if you're based on your range of the rewards, it will say some 12, 13, the values which it can take. It will based on the alignment of the query and response, it will yield single scalar value. Now, what does PPO tries to do is to maximize the reward while keeping the new model close to the old one. By this, what I mean is now you have an LLM. You are trying to fine tune it with reinforcement learning for better alignment. So the outcome of the new LLM should be better aligned model with with the same knowledge of the previous model. You should not see any knowledge loss. It should be better aligned, but should not see any knowledge loss. So if you are only focused on rewards, if you change the weights of the LLM or the parameters of the LLM a lot, it may the knowledge, the direction of the knowledge and the knowledge it has might be deviated. So we don't want that. So what we are trying to do is we are trying to keep the new model very similar to the old model in terms of knowledge, but it should be better aligned. So for a given x, this RL1 is the one which we are currently fine tuning. So given the query X, Y is the prompt from new one which we are fine tuning, and given a query X, Y is the prompt, Y is the response from the supervised fine tuned version, like before RL part. This is the LLM. So the probability of Y given X should be almost similar in both the LLMs, like the freezed LLM and the one which we are doing reinforcement learning based fine tuning. The parameters or the weight should not change much. So we are including a the new component in our objective. What we are saying is it should have high rewards, like given the query X and the response Y, it should have the high rewards. But if it is deviating a lot from the old one, if the new model which is trained on the reinforcement learning based feedback is deviating a huge from the old model, we should not do that. So we are just taking the ratio of how much it changed, how much it changed from the old one, and like logarithmic probabilities. This is the probability, so we are taking the log probabilities of that and subtracting it from the reward function. So our objective is we need a high alignment without loss of the knowledge. That means the new model should be very similar to the old one with better alignment. I hope the objective which we are trying to solve here is clear. Let's see the same thing in a with an image, like the visualization, like what exactly is happening. Just coming out from little math, and we will go back to there again. So initially we have this query. There is an LLM. So we're asking the query. There is this query. We passed it to the LLM. We got a response. Now we are evaluating it. We have the query response pair. We passed it to the reward model, and we got the reward. The reward model, like you might be using any of the technique like RLHF or RLAIF. Anything is possible here other than DPO. DPO is not the reinforcement learning based method. So now we have this now we are going to the optimization part. So the first two bullet points were done. We asked the LLM for a query, we got the response, then we paired it with the reward model to get the suitable reward. Now we are checking about the optimization part. So what we are exactly optimizing is we have the query plus response. Here the active model is the one which we are fine tuning. Reference model is also the same active model, but it was not fine tuned. Basically, we took the we freezed one model as the reference model, and same model we took and we are just optimizing it for the better alignment. So we have one reference model, we have one active model. So the same query is passed through both the active model and reference model. For the next token prediction, we got the log probabilities. Now we are of these log probabilities, we are taking the KL divergence, and we anyway has the reward. We are passing this reward and the KL divergence, which shows the shifts in the distribution of the weights, both to the PPO. This is what we are discussing. The rewards minus we want to ensure the new model was very similar to the old one. So this we are passing to the PPO. PPO is the proximal policy optimization reinforcement learning based method which we discussed. Now what does this PPO do is it will update the policy gradients to optimize the model for better alignment. So here comes the word policy gradients. So before diving deep into PPO, let's come back to the basics of reinforcement learning. First, understand what exactly this policy gradient is, like what we are trying to optimize and how does that work. So uh, uh, the entire goal of the policy gradient is to improve the policy, increase the likelihood of actions that led to high rewards, and decrease the likelihood of actions that led to low rewards. So just come back from the LLM point of view. Just think it in a game point of view. You are in the center of the screen. If you go right side, you will win the game and you will get reward of 10. If you go to the left side of the screen, you will lose the game and you will get minus 10 rewards. So what does this policy gradient try to do is it will write a policy. Policy is set of rules, you can assume. It will write a policy such that it increases the likelihood of actions that led to high rewards. So in this case, it will try to write the rules. It will try to update the policy such that it will go to the right side, win the game and gain the rewards, and it will decrease the likelihood, like it decrease the likelihood to go to the left side such that it will lose the game and it will get the -10 negative rewards. So this is the entire policy of the policy gradient. Now if we dive into the math, so don't worry about seeing these big equations or complicated equations. Let's break it down into the small parts. Now j of theta, this is very much the objective function. Even when we write the gradient descent or all this, we use the j of theta as the standard notation. J of theta will be our objective function. The e pi theta which we mentioned here, for now forget about this derivative part. E pi theta, this is expected value of, if you see in the statistics, this is basically expected value of the policy. Now, the theta represents the parameters of the policy. If you're training it for a neural network or LLM, it will become the weights of the LLM or the weights of a neural network. And if we see this log of pi theta ATST, the ST denotes the current state. So if you're on the middle of the screen, the state is you are on the middle of the screen identified by coordinates or some other way. And the action is whether you want to go right or whether you want to go left. So from the given state, what action you are taking. And this R of T is reward if you take that action. So if we combine this and see like if we take the gradient of this and see what we're exactly doing here is, the gradient of the log probability, what we are taking is, tells us how to change the model to make the given action from that state more likely or less likely. So we're just multiplying this all with the reward obtained to that action. So this entire policy gradient uh, comes down to increasing the likelihood of actions that leading to the high rewards and decreasing the likelihood of actions that leading to low rewards. I hope policy gradient law is clear now. I'm moving further to discuss about the multiple trajectories part. So when we can see here again, it is same. We have the log probabilities. Like this is the state I, and we have the corresponding action to choose, and we have the reward followed by. But what is this multiple trajectories is, we cannot compute a true expectation. What we told here is expectation of this. So it is so it should be ran multiple times. Let's say it should be ran infinite times, and it should be the expected value should be computed. But we cannot compute a true expectation because we need the infinite trajectories, and we cannot do that. So we use an average over m sampled episodes to estimate it. So we run over m episodes, and in each episode we sum over each time step. Like we define a time step, and over that time step, we'll sum over that. So we are averaging over it. So we get this 1 by m and I equal to 1 to m. So these are the number of episodes. T equal to 0 to t. This is the number of time steps. So the outcome of this is the gradient of the expected reward. This is basically the expected reward. If you remove the gradient, it is expected reward, and we are doing the gradient, so we are basically estimating the gradient of the expected reward. So this is what the multiple trajectory is about. I hope you are getting the difference between the like why we are taking the episodes, m episodes, and the t time steps in each episode, because we cannot estimate the true we cannot estimate the true expectation value of the entire policy. So we are doing some approximation which stays same. So we are just trying to use the limit and tends towards infinity. We are doing that same thing here. Now let's move on to this actor critic part. This may this is again slightly out of the policy gradient which I will discuss, but this will be helpful in PPO. So I'm basically building up the basics for PPO, so you can understand it in the LLM context much better. So we are familiar with the learning rate. This alpha again denotes the learning rate, like how much big step we are going to take to while we are updating the network. And we are again seeing a new component here. This is q of s of a. What we are saying is, for taking a given action from the state, so q of s comma a is the action value estimate from the critic. So we have one actor and critic. What does actor do is to act, and what critic does is it will criticize, or it will criticize the action taken by the actor. So in lame terms, it is as simple as that. But in most in both the actor and critic will be the neural networks here. So now if this value is high, is the QWS comma A. So to take that action from that state is high, the actor is encouraged to make this action more likely. So if the critic say, if critic the value given by the critic is high, then the actor is encouraged to do this in more frequently or most probably. This is all about the actor critic. And again, that theta which we're updating is the weights in the terms of neural network, or any parameters which you define in general. Now, another concept which is required further going into PPO is, till now, all we have discussed is in terms of rewards. But there is another terminology which is used, which is slightly similar to rewards, but different conceptually is advantage. We have two things. So let's discuss about what exactly are rewards and what exactly is advantage. So we are familiar with rewards now, but what exactly rewards tells us is, if you use the raw rewards, they only tells what just happened in the previous step, like what is the previous token predicted and how fair it, how correct it is. Now we can, for the long term we cannot do that. Let's say, let's go back to the chess game example. So if I have made a move, the immediate reward might be very high for me, but eventually I may end up losing the game because of that step. So raw rewards only tells about what happened just now, like what just happened in the previous step. They don't account for the long-term impact of the actions. My immediate step might be very good, but that might lead to the negative impacts in the future. So raw rewards are not accountable for that. So there is this concept of advantage. So what we do in advantage is, we try to estimate the long-term benefit. Like if we take a current action A from the state T, and if we follow this policy, what will my estimated future rewards look like? So advantage estimates the long-term benefit of taking action A in status, and that compares to the average action in that state. So advantage is defined as Q of SA minus V of S, which we're seeing here. And this V of S is the value of that state, the value of the state which you are in. And what Q of S is from this state, if you take an action, what will be your value? So uh, this Q of S is estimated by taking expected rewards of future as well. So if we can see, just focus on this RT. R is reward, and it is a time T. Now it is seeing into future T plus 1, T plus 2, and so on. And this gamma, what we call is the discount factor. So my immediate step is very much essential to me than my next to next step. So what I'm doing is, I'm taking the discount of the future time. So this is always less than 1. So for next step gamma, for next gamma square, gamma cube. So I'm discounting the rewards and estimating the expected value of the rewards, and subtract, this is the my long term benefit of taking that action. So it is estimating the long term benefit and subtracting it from my current state. I know the value of my current state, so I'm subtracting it from the expected rewards. So then we call this as the advantage. So the objective function for training the policy in PPO, the objective function for training the policy is based on the advantage function. We directly won't use the raw reward. Why is raw rewards has high variance? They don't account for the long-term impact of the actions. So let's move on to the PPO. Now, this PPO is in with reference to the LLM which we are doing. So just stay back and let's see. This is the same policy gradient which we used previously. If we keep an eye on this, this is the gradient. We're estimating the gradient of the log probabilities of action taken from a state, multiplying with the corresponding rewards. Now in PPO, there is slight change. Instead of rewards, the log probabilities of action taken from a state were there. But instead of this, we are instead of the rewards, we are taking the advantage of state and action. So which was previously defined. So advantage of taking action A from state S. So this is the policy gradient formula used for the advantage estimates in PPO. And there is one other important part in PPO which we need to discuss is the importance sampling. What exactly is importance sampling is we are training the training data comes from the pi theta old, but we are updating the new policy. We are using the reference model and the current model, but the training data is coming from the reference model. So to account for that, we need to adjust the importance sampling ratio. So basically, if I frame it better, when we say sample from a policy pi theta, we mean run the policy in an environment, collect the collect all the data, states, actions, rewards based on what actions the policy chooses. So sampling from pi theta is equal to using the current updated version of the model, like which is undergoing this reinforcement learning based feedback. And sampling from pi theta old is equal to using the previous version of the model before the latest updates. So what does this switch exactly mean? Like, so if we, in theory, the policy gradient should be the gradient of j of theta, and estimation should come from st comma from the state and action from the pi theta, not from the pi theta old. But in practice, collecting new samples every time a parameter changes is very expensive, very slow, and noisy. If we change the parameter and we updated our policy and we're again getting the training data from that, is going to be expensive, slow, and noisy. So instead of collecting new data after every small change to PPO, they are still collecting data using the pi theta old. Now there is this distribution change, so we need the importance sampling. How we are going to do that importance sampling, so I think why do we need importance sampling is clear, because the training data comes from the pi theta old and we are updating pi theta, the distribution has changed. To account for that, we adjust the importance sampling ratio. Now in the importance sampling ratio, what we are doing is reweighting the sample so it reflects how the new policy would have behaved even though it was collected under the old one. So if we see pi theta, the probability of action taken from a state S divided by the probability taken by the old policy, by the old model, by the reference model in the action A from the state S. Now we are doing the scaling. Such now, what does this division mean? Is this reweights the sample so it reflects how the new policy would have behaved. We are not using the new policy, we are taking the old policy and approximating it such that if we have used the new policy, how would have it behaved even though it was collected from the old one. So basically, in technological terms in the RL community, they call this as an off policy approach because the training we are training the new model and using old old models behavior data. So that's why the important sampling is one of the essential ones. Now continuing from where we left off, so we have this advantage. This part is expensive to compute every time. We approximated it from the old policy. This is the gradient which we have taken, and this is the objective function. If we take the gradient of this, we'll see this. So off policy objectives became this part. I hope I'm clear. If there are any questions, please ask in the comments or Q&A. We can discuss it at the end. Now, the major contribution of the PPO in the algorithmic part comes from this clipping. PPO has something called as clipped objective. What does this mean is, don't get carried away by seeing a lot of variables here. But let's understand what exactly is this. We anyway have the RT into the advantage we have. RT not previously we this ratio is became as this RT of naught, and we are multiplying it with the advantage. So RT of naught is the ratio which we took. A is the estimated advantage. This is anyways there as our previous objective. But what change we made to the previous objective is we are clipping something. So what exactly we are clipping here is we are taking the probability ratio which we have and clipping it from 1 minus e to 1 plus e, and anyway we are multiplying it with the advantage. So what we are trying to do essentially here is we don't want to deviate a lot. uh, uh, the small number epsilon used in the original PPO was 0.2. If this probability ratio should be between 0.8, the result should be between 1 minus e and 1 plus e. If it is going below that or going above that, we are going to clip it. This helps in handling the variance. This helps in handling the noise. If there are because of few data points or because of few things, if the model behave, we are updating the parameters very drastically. This helps us in not doing that. So this helps us in avoiding the training the model with outliers or the noisy data. So this is one of the main contributions of the PPO. It looks very simple. If we go from the policy gradients to the importance sampling to here, we are just taking minimum of everything. If just we are clipping the upper bounds and lower bounds. If it is less than lower bound, we are taking the lower bound. If it is greater than the upper bound, we are still taking the upper bound. So this is what the clipped objective of PPO is. So till now, what we discussed is in general, like how the PPO, the policy gradient, and then when came till PPO and discussed the math behind it. And for the next 10 to 15 minutes, what I will do is connecting all the dots. We started we started from fine tuning an LLM using reinforcement learning, and we discussed RLHF, we came to RLAIF, then we went to DPO, and then we came back to RLHF slash RLAIF again. And here we discussed how exactly the math behind the policy gradients and the math behind PPO. Why are we doing this? And we are in a state appreciating the entire architectures and design decisions taken at every point. Now the to conclude, like we need the dots connecting. You explained me PPO, you told this, but how this is connected in the LLM scenario. So let's close this with one bang, like the connecting all the dots which we have learned till, and pay super attention to this image. Most of the things will be clear. So we are the user. There is this user. There is this user query here. Now a user query. Let's take some example, like write a poem about AI in the style of Shakespeare or something that was given to the policy LM. So what exactly is policy LM? The LLM which we are trying to update here. Now this query goes into the policy LM, the current version of the model which is being optimized. Now, what does policy LM do? The model outputs a response Y, that will be Y1, Y2. There are many response of that to the query. Now, the example output for that might be some O circuit, some output from the policy LM. We name it as Y. Now, the pair X comma Y is divided into states and actions, and these were fed into multiple parts. If you observed it carefully, the state st and the action at, query plus past tokens is the state, and action which the policy LM should take is the next token. Previously we discussed with a screen example of moving right left, but now in the LLM scenario, the state is query plus past tokens, and the action should be what next token the LLM should predict. Now see carefully in the entire image. We are still here. We have the user query, we have the policy LM, we have just given the X and it responded with Y, and we concatenated this X with Y, and we have the state and we have the action. Now who all are storing these tokens? Like each token generated is treated as action, we discussed. Now these state action pairs are fed to reward model. We discussed previously, reward model will say how aligned X and Y are. the query and the responser. So the state action pairs must be fed to the reward model, and it should be fed to the value model. What does value model do? Value model gives the value for the one in the value of the current state. So if we have remembered, so we have the state and action pairs now. We It should be fed to the reward model one. It should be fed to the value model because it should know the value of the state, which we discussed in the advantage function. And these are also being fed to the experience buffer. This is the new term which we are hearing now, experience buffer. This is fairly common in reinforcement learning part, but we didn't discuss it yet. We will come on to that. Now, from the policy LM, let's move on to the next step from this way. So we are at the reward model. Now, what the reward model does? Reward model predicts a scalar reward from the full x comma y response pair. It was trained using the human preferences, so it will give some reward to that. If humans preferred output A to B, reward model assigns higher reward to A and less reward to B. Now there is this value model. It estimates the expected future reward. So we are moving to this SFT part, the supervised fine tuning model trained before RLHF on curated human preference data. Now we are using this to compute the KL divergence between RL model and RL model and the SFT model, which we discussed previously. Instead of taking only rewards, we are doing the rewards minus some constant beta into log probabilities of predicting y given x, so that we don't have the huge deviation from the reference model and the one which was tuned through reinforcement learning. Now we are clear with this policy one, how the states and actions are computed. SFT, KL divergence, we are clear. Reward model, we are clear. Value model, we are clear. The left part is completely clear, and we are at the center now, which is GAE, generalized advantage estimation. So this is the one which we discussed in the PPO, like how we are doing that advantage. If you see this properly, advantage of state A comma action is given as like the discount factor which we discussed, that was given. And this is the core RL tree to compute the advantage in the LLM scenario. So what we are doing here is there is a few things called as TD error and return. I will come back to this later. Like these are the this combines the rewards and the value prediction, and the return is the advantage which we have plus the baseline reward of that state. And we are pushing those advantage and the baseline rewards to something called as experience buffer. So now this experience buffer stores the tuples of state, action, policy of the old, and the corresponding advantage and the returns. So this experience buffer is basically used for batching data. So if you think it in the naive ML or ML form, in the deep learning format, we have the iteration. So we have the epochs and iterations. We have so this is similarly you can understand in the experience buffer. So for batching the data, we'll sample from the experience buffer and we'll batch the data and we'll do the PPO updates. So experience buffer is used for only batching the data, nothing else. Now, if we move to the fairly right side, we have the policy LM with pi theta RL. So this is the current model. It is getting updated using many losses. One loss which you see is PPO clip loss, which we discussed already, like how advantage and the information sampling was done, and then we are multiplying with that and clipping it to some lower threshold and upper threshold. So this PPO clip loss. There is one LM loss. This is for pre-training corpus to retain the normal language efficiency. It was pre-trained before, and it should not lose that information. So this is the pre-training data, and we have this LM loss. And KL penalty is anyways coming from the compared to the SFT to stay the human aligned, that is coming from reward minus KLT. That KL penalty loss is already coming. And there is one, these are for the policy LM which is updated currently. And we have the value model here. Now the value model is also updated using the MSC loss. Between what? Between the prediction made at that state and the estimated returns. So the estimated return is coming from this GAE, and we are making the difference between taking the MSC loss between the value that at the current point with the returns it should have got. So if we summarize all the losses, P4 clip loss, it is optimizes the model using RL. KL divergence is used to prevent model from becoming too weird or different from the original one. LM loss is keeping general language skills. MSC loss is improving the value estimator. So if you again summarize this GAE part, like why exactly GAE is used, and uh, if we discuss that, raw advantages, the raw advantages which we estimates can be still noisy or unstable. GAE smooths them by using the weighted sum of temporal differences. If we see what exactly is having in the TD error, TD error is termed as temporal difference error. So it is the difference between observed reward at state ST, comma taken action AT, like observed reward plus expected future value and current estimate of the value. So if we see RT, this part is reward at time step T from the reward model. V of ST plus 1, this is value of the next state. V of ST is the value of current state. So what we're interpreting here is, was the outcome better or worse than the expected? Expected is the average of the all. And when we discuss about the return part, like the estimated total future reward, this is not the estimated total reward, but it's the estimated total future reward. This combines the advantage with the baseline value predicted by the value model. So what exactly this tells us now? What total reward can we expect from this state considering both current expectations and recent improvements? So this is trained using the target of like this MSC loss. It just does the RT minus like basically RT minus VST whole square. So this is how the entire fine tuning moves from the policy LM of the old and updating various losses and all this. So I hope these are the references used. Like mainly these are open sources. The images which I use, the equations which I got, these are from various blogs and things by many AWS blogs and Google Cloud Program and TRL Python library and all. Thank you for your time, guys. If you have any Q&A, we can do that.